All right, so we're on the top of page 7, and the reason why we're here first is because I want to talk about when you cannot differentiate a function or when you cannot find the derivative. So there's 3 ways for a function to fail to be differentiable, meaning you cannot find the derivative at a given point. And we've talked about a couple of these indirectly. The first one is at a sharp point, and I'll talk about that in just a second, or a cusp, which there's no graph for that. So a graph of a cusp is when you're taking a limit and the values are approaching either positive or negative infinity, so the graph would look something like this. So it's curved in this direction, and it's curved in this direction. Okay, so it's not a straight line, and then they come to a point. Okay, so this is a cusp, but this is a graph of a cusp, not a bird. Okay? Then we've talked about the absolute value graph, and this is an example where you could identify, if I was looking here, the slope at this point, right? Whatever it is, you'd use what, rise over run? Or maybe right here, or over on this side, you could describe what the slope was. But if I asked you to take a look at the slope where x in this case is equal to 0, it's not always going to be 0, it's wherever those 2 line segments meet to create this graph. I could say the slope is 0, true? Or I could take my ruler and I could just turn it like this. Couldn't I say the slope is, I don't know, negative 1/2? Or I could say negative 3 if I made this even steeper. Or I could make my slope positive. So if you notice here, I have an infinite number of slopes at that point. That's the problem. So in this case, where x is equal to 0, this point right here is not differentiable. Now remember, when you have an absolute value graph, it can be moved around your coordinate plane. So it's not always going to be at 0, but it's where your vertex is. So here, at this point, your function is not differentiable because you have an infinite number of slopes at that point. Anywhere before and after, totally. Okay, but there you cannot calculate a slope here. Okay, same thing with this, where you would have a sharp point there. Another place where a function would be discontinuous, and we did talk about this, was if you have a jump, a hole, or an asymptote. So when the function is discontinuous. So the example that we gave here was where you have a vertical asymptote. And again, in this case, it's where x is equal to 0. Okay? But you can evaluate the limit. But if you take a look at the limit as x is approaching, in this case, 0 from the left and 0 from the right, at 0, does the limit exist? No, because from the left you're going to negative infinity, and from the right you're going to positive infinity. So any place where you have a vertical asymptote, or you have a hole, okay, and you have to basically pick up your pencil to sketch the graph, right, because you have to jump over that hole, or a discontinuity of some kind of jump. All right? And then the last, which actually there is a question like this on your homework, when you have a vertical tangent line. So think about it like this. Okay, if this is f of x and we want to look at the slope, so we're looking at the derivative. Here I could say, just in general, the slope is positive, right? Just like that exercise that you guys did the other day. Slope is positive, slope is positive, slope is positive, slope is really positive, it's getting even more and more positive. And then what happens here? Tell me about the slope right there. It's undefined, right? Vertical lines have slopes that are undefined. Horizontal slopes are 0. So then as I continue along this graph, the slope is still positive, 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 positive. Does everybody understand what I'm saying? So we're any place where you have a vertical tangent line to the graph. So in this case, it's right here. Okay, the slope is undefined, therefore it doesn't exist. So this looks very similar and an exaggerated version of what? The cube root of x? Okay, so that's an example of where you'd have a vertical tangent line. Oops. Okay, so this is where your function would not or would fail to be differentiable. All right, so we're going to jump back to page 6 so that I can talk about when you can't take the derivative. Okay, so we're on the bottom of page 6 when we're talking about differentiability. Okay? And then we're going to talk about the graphs up top. All right, so first of all, they're saying that the derivative at A exists yes. If it does, then the tangent line to the graph is at that given a value. Okay, so you were asking about a. So let's say if I said a is 2. So you're saying that the derivative at 2 would exist, okay, and the tangent line would go through some given point, 2, comma, whatever the corresponding y value is, and we would have that line that was tangent to the given curve provided we had the function. Does that make sense? So this a value is a specific number. They would have to give it to you for you to evaluate it. Okay, if f prime of a doesn't exist, okay, I gave you a few scenarios in which that might occur. They're saying it could be a vertical tangent line, or it might not be unique, where you have a sharp point or a cusp. Okay, so to say that a function is differentiable, okay, means that the derivative exists. So eventually what you guys are going to see are questions that say things like a twice differentiable function. What that means is you can take at least the derivative 2 times. Maybe more, maybe not. But they're telling you you could take it at least twice. Does that make sense? It doesn't mean that you're looking at the second derivative. It's saying f of x is a twice differentiable function. It means you can take the derivative of that function at least 2 times, if not more. So they're saying that the derivative is defined. Does that make sense? Okay, so they're it's just like when they said the function is continuous. You know in your mind that when you're sketching that, you don't have to pick up your pencil. Okay, there's no jumps, no holes, no gaps, nothing. Okay, and if the function is differentiable on a given interval, it is differentiable at any number on that interval. Okay, so if they say it's differentiable from 1 to 2, any decimal from 1 to 2, you can take the derivative. Okay, beyond 1, beyond 2, you have no idea because I didn't tell you. It's not defined for you. So in this given theorem, this is definitely important to know. If f is differentiable at a given point c, then the function is continuous at c. Okay, so in order for a function to be differentiable, meaning you can take the derivative, it has to be continuous. Okay, and in order for the function to be continuous, the limit must exist. So you got to think back to the definition of continuity. So they're saying here, if the function is differentiable, then you can imply that the function is continuous. Therefore, the function's limit would exist. Go backwards. Okay, so in order for us to determine if a function is continuous, the limit of that function has to exist at a given value, right? The limit from the left and the limit from the right, and what's the other key point? One more time? Well, they do have to equal each other, but what else do they have to be equal to? F of whatever that point is, right? F of c, f of a, whatever your value is. Therefore, the function would be continuous, and if the function is continuous, then you can take the derivative. Now, can I say that if the limit exists, then the function is continuous? Is that always true? Is it just because this big fat X is here, or do you understand why? Okay, so let's say I have a graph like this. What's a scenario in which the limit would exist, but the function's not continuous? Yeah, if you have a hole there. So if I have a hole right here, and my graph approaches the same value from the left and from the right, but the function's not continuous, right? So in order to get over that hole, I'd have to pick up my pen or my pencil or whatever I'm drawing with, right? Okay, so this is why this is false. Because the limit could exist, but that doesn't necessarily mean that the function is continuous. So then if the function is not continuous, you cannot take the derivative. I can't take the derivative here. You guys might recognize this if you had Mrs. Kim last year. D, C, and L, like this. If the function is differentiable, then it is continuous, and the limit exists. Did someone have a question? Yes?
So is there a point where it can be continuous but not differentiable?
Well, think about the absolute value graph. There are a multitude. So if I were to sketch that graph, I mean, literally, if I'm thinking about it in terms of just being super simple about it, forgetting about the limit and the point and whatever, if I sketch this graph, did I pick up my pen? No. So ideally, if I'm sketching the graph, it is continuous. However, there are so many, like right here, this statement says that the slope may not be unique. So the slope is not unique here, because remember I took the ruler and I could have so many different slopes there. Okay? So in this case, the slope is not unique here, but it's unique here or over here. Okay? Or even with a cusp, if I was just sketching the graph like that. I didn't pick up my pen, but the slope is not unique at that sharp point, that cusp. Okay? So then here they're just talking about the contrapositive being true, where if the limit does not exist, then the function is not continuous, therefore not differentiable. Okay, and that should make sense based on what we talked about up here and this graph right here. Okay, so in terms of deciding if a function is differentiable or not, does anyone have any questions? Are you sure? Okay, because we're going to talk about these graphs here.